Our first example we took from chapter 21 is the loop that is centered around the x-axis, and we want to know the potential at this point P. So we want to find V at point P based on this loop. So the first thing we need to do is think about our differential length, and we're going to have to differentiate or to integrate around this loop. Another thing we need to think about is this distance r, and that's equal, because of symmetry, to the square root of x squared plus r squared, because of the triangle that it makes. And now I need to think about what is my differential charge. Well, that differential charge over the total charge is equal to the radius times the differential angle. This is just dl, differential length, over 2 pi times r, which is the circumference of the loop. And the r's are going to go away, and I multiply q up. That gives me differential charge is equal to q d theta divided by 2 pi. Now I can put this into my potential formula, and I'm going to have the integral from 0 to 2 pi, because I'm going to integrate it around the loop, of dq over 4 pi epsilon naught r, little r. And I can take out some of the values, and I can substitute for r. R is going to be a constant. So I'm going to have 1 over 4 pi epsilon naught square root of x squared plus big R squared, the integral from 0 to 2 pi of q d theta over 2 pi. So the q is going to come out, denominator stays the same, and now I have the integral from 0 to 2 pi of d theta over 2 pi, and that integral is very easy to calculate. And that's just going to be theta over 2 pi from 0 to 2 pi. Well, that just makes this integral result equal to 1, and my potential is equal to q, the charge around the loop, divided by 4 pi epsilon naught square root x squared plus r squared. And that is our result.